Hello, everybody. Since we've now hit 12 o'clock, I guess we should go ahead and get started. So my name is Pete Meyer from SB I'm filling in for Jason Key. Our webinar speaker today is Frank Delaglio from NMR, who will be talking about NMRPipe, and this being part 2 of his tutorial. For upcoming webinars, you can read there on the slide there. The January webinar has been postponed for simple with times, and February will be Orca. If you've got ideas for future webinars, then please let us know. And if you have any questions during the talk, there should be a group chat window. Please type your questions in there and we'll pass them on. With that, I will turn it over to Frank.
Thanks very much, Pete. Frank Delaglio here. Thanks very much for joining, and thanks to SB Grid for making this and all the other excellent structural biology software available for everyone's use. So last week, we talked about some of the concepts behind signal processing with special attention paid to non-uniform sampling. After a quick technical check, systems check for the SB Grid folks. All well.
Systems look good for me.
Very good. So as I was saying last week, we talked about some of the theories of signal processing. Today we're going to talk about practical details of signal processing and how to use the tools in NMRPipe to convert a spectrum from the spectrometer format to the NMRPipe format, how to process it, inspect it, do peak detection and display of such spectrum. So that's going to be today's overview. The lecture notes from last week and today can be found on the NMRPipe website, as well as software downloads and demo data archives of all the data that we'll see today in the discussions. Now, as most of you probably know, NMRPipe is script-based. We build scripts, usually C# scripts, full of processing commands, and we use various graphical interface tools inside the NMRPipe system to view data, choose processing parameters, and so on. And so in a usual NMRPipe workflow, we commonly move back and forth between the Unix command line, where we manipulate and edit scripts and execute them, and graphical utilities like NMR Draw. So we're going to see what that looks like, and we're also going to look at some new alternatives that will allow us to do all of these steps completely in a graphical interface. We're also going to see the specific workflows for non-uniformly sampled data. As we discussed last week, there are special reconstruction methods that are needed in order to take advantage of non-uniformly sampled data. But in a typical workflow, we recommend that once we convert non-uniformly sampled data into the NMRPipe format, that we do an ordinary Fourier processing scheme first to confirm phase correction parameters, Fourier transform details, and so on. And only then, after all of those parameters have been established properly, do we do a complete reconstruction with a special reconstruction method like SMILE or IST. And we will see examples of that today as well. Now, the key steps of spectral processing as we use them in NMR, pretty much common to all the dimensions of a multidimensional NMR experiment, is that we apply a digital filter. We also call that a window function or an apodization function. And in the process of applying that window function, we also adjust the intensity of the first point in the time domain data. We'll talk about that. And we employ zero filling, which is adding a collection of zeros to the end of the time domain data. And then we apply a Fourier transform and phase correction. And that's more or less common to every direction of the data, both the directly acquired dimensions and the indirect dimensions. In NMRPipe, we do that with a Unix pipeline of commands. Pipeline is a construct where the output of one program is used automatically as the input to the next program in a series. And so when we use NMRPipe, we string together lists of different processing functions in a pipeline, for instance, a window function and a Fourier transform, and a stream of data vectors makes their way from one program to the next, and each program applies a different aspect of the overall processing scheme. That leads to processing schemes that looks like this. This is a Unix C shell script with a three-dimensional processing scheme. So there are a lot of nice advantages to this. We can manipulate a scheme like this with standard tools in Unix, text editors, and so on. But for someone who's never seen a Unix shell script or doesn't know much about NMR signal processing, it can be an incredibly steep learning curve to make sense of a script like this, and then to edit it and adjust it as needed, where we commonly have to do things like adjust the first point scaling and phase correction parameters, change the region of interest to suit our specific spectrum, and so on. But once we're comfortable with this scheme of doing things, there's almost no limit to what kind of processing and analysis that we could do with NMRPipe, because we can rearrange all the processing and analysis components in scripts. That said, as we mentioned, this is kind of complicated, so it'd be nice to have alternatives. And the importance of alternatives becomes larger as we introduce other processing schemes for non-uniform sampling, where we have to do a lot more than just Fourier transform the data. And so what we've done is introduce a series of special purpose commands which will perform a complete processing scheme as a single command, or generate the NMRPipe C shell script that contains all the processing commands needed to do a particular processing task. And so we're going to see examples of commands like these during the demonstration. Now, as we mentioned, key steps of spectral processing: window function, zero fill, Fourier transform, phase correction. Here's what they look like in NMRPipe. We have the name of the function that we'd like to apply, in this case, a window function or a zero fill or a Fourier transform. And then also on the command line, we have whatever parameters are associated with that particular processing function. So for example, for phase correction, we have a zero order phase correction value and a first order phase correction value. Now, in the case of window functions, as we discussed last week, we generally apply window functions either to broaden or sharpen the corresponding lines in the spectrum. And by broadening the signals, we can reduce Fourier truncation artifacts at the expense of reducing the intensities that we see in the spectrum. By using a line sharpening window, we can make the lines look sharper, but at the expense of also reducing signal and actually increasing the size of the Fourier truncation artifacts. So that's something that we do during processing. And an obscure but important aspect of applying window functions and Fourier processing is that we have to scale the first point in the time domain data. And Fourier math tells us that the intensity of the first point in the time domain is the same thing as the integral of the corresponding spectrum. So adjusting the first point in the time domain has the effect of adding or subtracting a constant in the frequency domain. What this means is if the first point is not scaled properly, there will be a baseline offset in that particular dimension. So for example, in this case, if the first point is not scaled properly, we get a spectrum like this with constant baseline ridges. If the first point is scaled properly, we get a spectrum with a nice flat baseline everywhere. The rule of thumb is simple. If there's no first-order phase correction in a particular dimension, you scale the point by half. The reason for this is interesting, and you can find an explanation for it in the presentations at the NMRPipe site, but we will skip over those particular details and just note that this is something that you have to do. If there's no first-order phase correction, we scale the first point by half to avoid a baseline distortion. Now, in the case of zero filling, as you know, in an NMR acquisition, in each dimension, we generally measure complex data. That means we measure a real component and an imaginary component. So in a particular indirect dimension, let's say we might measure, in this case, 16 real points and a corresponding 16 imaginary points. And it's customary when we get ready to Fourier transform data like this, that we append a series of zeros to the end, zero filling. So in this case, we have 16 real points followed by 16 zeros and 16 imaginary points followed by 16 zeros. One of the reasons for this is that when we Fourier transform the data to generate a spectrum, the result of the Fourier transform is also complex. It has a real part and an imaginary part. But in practice, we only analyze the real part, and we generally discard the imaginary part. If we don't perform zero filling to at least twice the original size, when we discard the imaginary part after a Fourier transform, it would mean that we've thrown away half the data. So here we've measured 32 total points. If we want to retain the information content, we have to end up with a result that has at least 32 points as well. So if you don't do zero filling, you'll be throwing away half of the signal content of the originally measured data. And the tools that we use to take a real-only spectrum and reconstruct the imaginary part, that tool is called a Hilbert transform, that will only work properly if you've zero-filled the data by at least once. So 2 important reasons to make sure you always zero-fill during processing. And so these things lead to a set of rules of thumb for spectral processing, which previously we would hold to by editing the scripts by hand and doing things like adjusting zero filling and first point scaling and so on. What I'm going to show you is that these new commands that we have for generating processing scripts will take care of those details automatically. So for example, here's some example data, a 2D proton nitrogen experiment, and it was processed with this single command. Generally speaking, we just specify phase correction parameters, perhaps a region of interest, and maybe some Fourier transform options. So this single command generates this complete processing script, and the important details like first point scaling and zero filling are set automatically. So here's what a normally processed spectrum looks like. Now let's look at some alternative cases. In a typical proton nitrogen experiment, the peaks commonly fall on a very rough diagonal because there's a correlation between amide proton chemical shifts and amide nitrogen chemical shifts. So you see a kind of general trend of chemical shifts from one diagonal to the other. Now, in the indirect dimension of an NMR experiment, there are actually separate experiments that are performed to measure the real part and the imaginary part. For Fourier transform math, the real part is supposed to be a cosine term, and the imaginary part is supposed to be a minus sine term. But depending on the details that are used to convert the spectrum or how the pulse sequence was written, sometimes the sign of the imaginary data gets set positive instead of negative. And when that happens, you get a spectrum that looks like this, with one of the dimensions reversed. When we see a case like this, we have to adjust the Fourier transform so that the imaginary part of the data is negated before the Fourier transform, so the spectrum is reversed. Likewise, there are some pulse sequences that arrange an indirect dimension so that the normal center of the spectrum is rotated to the edges. This is commonly done in a states TPPI experiment. This corresponds to changing the sign of every other point in the time domain data. Sometimes this sign adjustment is accounted for in the pulse sequence. Sometimes it isn't, and we have to account for it during processing. So this is another common adjustment to a processing scheme. We use a Fourier transform mode, which first alternates the sign of every other point before doing the Fourier transform to avoid a case like this, where the two halves of the spectrum are rotated to the edges, like we see here. So, two practical points. And as we're going to see, the basic form of these processing commands stays the same for both conventional and non-uniform sample data. And by only small adjustments, we can do lots of different things. So for example, if we have a command like this to do basic processing of a three-dimensional spectrum, if we'd like to do linear prediction in both directions, let's say, we only have to add a few additional arguments. In this case, we say in the y-axis, we'd like to do forward-backward linear prediction. And in the z-axis, we'd like to do Fourier forward-backward linear prediction with a 12th order linear prediction polynomial. Last week, we talked about ways to use the reconstruction techniques that are usually applied to non-uniformly sampled data and apply them to conventional data as well as an alternative to linear prediction. So if we'd like to do that, we only need to add a couple of extra arguments. We call this NUS-style extrapolation NUS zero fill in NMRPipe. So just by adding a couple of arguments, we can either do this extrapolation using the IST reconstruction technique or the SMILE reconstruction technique. And we'll see examples of that soon. And finally, as mentioned, the reconstruction commands for non-uniformly sampled data take very similar arguments. So for example, if we had a non-uniformly sampled 3D spectrum, we would do an IST reconstruction with a command like this. And as you see, it has arguments that are a lot like the ordinary Fourier processing command. What this means is that it will be very easy for us to do trial processing with a regular Fourier transform scheme and then do a complete reconstruction with a more time-consuming method like IST or SMILE. And then finally, we're going to see how we can actually manipulate all these commands inside a new graphical interface that's part of NMR Draw. So that's the slide portion right now, and we're going to move to the actual software demonstration. To start with, we're going to work with a two-dimensional proton-nitrogen spectrum. And for those of you who have used NMRPipe before, you're familiar with the idea that the first step in our workflow is to build a script that converts the spectrometer format data into the NMRPipe format. For Bruker data, we do this with a command called Bruker. For variant data, we do this with a command called variant. This is data measured on a Bruker spectrometer, and so I'm going to type the command Bruker at the command line from the directory where all the spectral data is. And when I do that, I get this graphical interface. So the first thing I do is select the name of the file that I'd like to convert. For Bruker, that will be an SER file. And now when I start the interface, you'll see there are a few default settings. One of the key things that we do during conversion of the data from a spectrometer format to the NMRPipe format is to establish the chemical shift calibration information for each dimension. Now, in the default calibration scheme that we use in NMRPipe, we assume that the center of the directly detected dimension is centered on water, the water signal. And we use a calibration curve for the chemical shift of water at a particular temperature to decide what the chemical shift of the center of the spectrum should be. And then we propagate that chemical shift calibration to the other dimensions based on the gyromagnetic ratio of proton to nitrogen and carbon. So when we first start the interface, the parameter setting for temperature says that we will take the temperature setting from the parameter files of the spectrometer. And the setting for the center position in ppm of the directly detected dimension, what we call the x-axis, is set to H2O. So in other words, it will be whatever the chemical shift of water is at the given temperature. So I've selected the data that I want to convert. Now I'm going to press the button that says Read Parameters. The interface will read the pulse program and the various parameter files and attempt to determine all the important conversion parameters. And it will highlight those that we need to pay some attention to and perhaps adjust interactively. Now, the reason for this step is critical because depending on how the pulse sequence was written and implemented and used, the parameters recorded in the spectrometer parameter files may not accurately reflect the actual parameters that we use to measure the data. This is especially true for older hand-built pulse sequences, whereas the newer pulse sequences supplied by the manufacturers will often have these details established correctly. That said, it's a common circumstance, especially for Bruker data, that the temperature that's recorded in the parameter file is not an accurate representation of the actual temperature that was used to acquire the data. So if that's the case, here's what we do. In the temperature entry in this interface, I will type in what the correct temperature should be. And back in the center position in ppm of the directly detected dimension, I'll use the menu to set that value back to H2O. So I've set the temperature manually to the correct value, and I've set the center position back to H2O. And now I'm going to read the parameters again, a second time. And that will calculate a new chemical shift for the center of the spectrum, and the other chemical shifts will be adjusted accordingly. So small detail, but very convenient. And now I will save the script on the disk and execute the script to convert the data from the NMRPipe format. It just takes a second, and we're all ready. So as the next stage, what we would commonly do is run the NMR draw program, and that will display our time domain data. And if I go back to the command line, if I want to, I can run one of these basic processing commands. So I'll just type basicft2.com with no other arguments, and that will generate some kind of spectrum. And in fact, it also built a script. Here's what the script looks like so far. It doesn't have any phase correction values or Fourier transform options. So if we look at the spectrum it generates, this is what it looks like. It's not phase corrected, and the Fourier transform options are not set correctly. What I'm going to do is show you a new interface inside NMR Draw, which is an alternative for this kind of command line work that we're going to do. And in the conversion interface, you'll see a new option which says Run NMR Draw in process mode after conversion. So I'm going to turn that checkbox on. And now after I convert the data, NMRPipe will be run with this new processing interface. So here it is, processing parameters on the left-hand side, spectrum on the right-hand side. So first, a few general notes about using NMR Draw if you haven't used it before. You have a command panel at the top with some different pull-down menus. And to activate a pull-down menu, press and hold the rightmost mouse button and then select an option. If you click with the left mouse button, you get the default menu item, which is whatever is first in this pull-down menu, which in this case is the command to view 1D horizontal slices from the data. And each of these commands in the menus has a one-letter keyboard shortcut. So for example, if I want to turn this mode off, I see in the menu that it's E to exit. So I can just type the letter E at the keyboard to turn that viewer off, or type H to turn the horizontal slice viewer on. Now, whenever the mouse is active at doing a particular job, the top border of NMR Draw tells us what the left, middle, and rightmost mouse buttons do. And generally speaking, the mouse will perform one set of actions when the mouse pointer is inside the spectral drawing area, and it will perform a different set of actions when the mouse pointer is in the border. So for example, according to these messages, when the mouse pointer is in the border, I can drag the center mouse button to change the vertical scale of the data, and I can drag with the rightmost mouse button to change the vertical offset of the data. And so I can use the mouse to scan through the data and look for a particular 1D slice. And you might notice in the command panel, as I drag with the mouse to look at different slices, the particular slice number changes in the command panel. And if I want to, I can type a particular number, like 1, to look at the first 1D slice in the data. So here is the first 1D slice from this two-dimensional experiment. If I'd like to establish some processing parameters, I'd like to Fourier transform this slice before we continue. And so in this processing pull-down menu here, I will choose the command that says auto process 1D. And that will apply a predefined set of functions, window function, zero fill, Fourier transform, and I have data that looks like this. So now in the command panel, I can turn on interactive phasing with this button, and then I can use the sliders in the panel to change the zero or first order phase corrections. And I can either drag the slider to change the phase value continuously, or I can click on the slider on one side or the other of the slider bar to increment or decrement the phase. Once I'm satisfied with this, you'll notice that the phase correction value I selected in the command panel is also inserted in the processing panel. And so I'll press this button, Update Script, and that will generate a processing script based on these parameters. If I want to, we can look at this script with the button that says Edit Script. So here's what it looks like. Here is the single command that was used to generate the processing scheme, and here's the actual processing scheme that was generated. So now I will execute this script to generate a spectrum, and here's what it looks like. So the data are nicely phase corrected, but we have this issue that we spoke about before, that the two halves of the indirect dimension are rotated to the edges. So when that happens, we have to adjust the Fourier transform options for the indirect dimension, for the y-axis. And I will turn on this checkbox that says rotate the two halves of the spectrum. So click that checkbox, update the processing script, and execute the new version of the processing script. And there it is. So we have a beautiful spectrum. It's nicely phase corrected. All of the Fourier transform options are set the way that they should be. So let's say that we'd like to add linear prediction to this processing scheme. In the processing window, I'll just use the checkbox here to turn linear prediction on. If I want to, I can adjust the linear prediction order. By default, the mode is mixed forward-backward LP. I'll update the script and execute it. And there's our linear predicted result. Come in here, have a look. Nice. Suppose instead that I would like to use one of these non-uniformly sampled methods to do the interpolation instead. So I can do that in the processing window with NUS-style extrapolation, and I'll turn it to IST. So now instead of using linear prediction to extrapolate the data, we'll use the reconstruction method called IST. So I'll update the processing script accordingly and now execute it to generate a new version of the data. Now here are the IST iterations. And there's the corresponding result. So also looks nice. And the lines are just a tinier bit narrower than they were in the linear prediction case. But we'll see some other side-by-side examples in a little bit. So that's a conventional 2D example. Let's look at a 3D example. In this case, this is an HNCL experiment. And I've already built a conversion script, so we won't bother to do that again. In order to run NMR draw in this new process mode, we include the command line argument -process, and we have to explicitly name the time domain data that we'd like to use. So here's what we get. Here's the first plane of the time domain data, and just like before, I'll view a one-dimensional slice, look at the first slice in this data. I'll use the autoprocess 1D command to convert it into a spectrum. I'll turn on interactive phasing and adjust the phase correction value for this 3D data. So I like that value. So now I will update the script, and we can look at it. So here's the single command that was used to generate the script, and here's the complete 3D processing scheme that we built so far. I will execute this script. And now we have a 3D result. I can look at the XY projection of this 3D data, and look, it's not phase corrected yet in this carbon dimension. I can look at the XZ projection, which in this case is a proton-nitrogen dimension. That looks good. And if I want to, I can look at the YZ plane, so in this case, carbon-nitrogen. So I see that this data still has phase correction in the indirect dimensions. So how can we phase correct that? If we want to do this interactively, now I'll use the mouse menu to look at a 1D vertical slice from this data. Like, let's say, for example, this one. And in the 1D menu, I'll use a command called append 1D. That will keep this particular 1D vector on the screen so that I can select other ones at the same time, like this one. And now I can use the mouse to move a phase pivot to point to one particular peak. And I'll use zero order phasing to phase the peak at the phase pivot. And I'll use first order phasing to phase the peaks everywhere else. Okay, when I interactively phase correct these vectors, what I notice is that the first order phase correction is pretty close to 180. Generally speaking, it means that the spectrum was probably set up so that the phase correction is exactly 180. So if you don't know what the phase correction values are, you should always give it a try with standard phase correction values like -90, 180. So I see that kind of phase correction is needed, and I'm just going to set it exactly to 180-degree phase correction. I'll update the processing script again and execute it to generate a new spectrum. So here's the XY projection of that result. It looks beautiful. Here's the XZ projection of that result. Also looks great. Here's the YZ projection. Looks very nice. And now there's a button in here I can press, and we can view strips from this spectrum. In this strip display, we have a pair of strips at every proton-nitrogen position. The proton-nitrogen positions were derived automatically by doing peak detection on the proton-nitrogen 2D projection of the 3D data. And so this strip plot gives us a beautiful overview of more or less the entire spectrum, because we can see the peak profiles in all three dimensions, in the proton dimension, in the nitrogen dimension, and in the carbon dimension. So, handy way to look at the data. Looks very nice. So let's go back now and add linear prediction in both the y-axis and z-axis. These check marks. So now I will update the script accordingly. Now the script is more elaborate, because when we linear predict 2 dimensions of a 3-dimensional experiment, we use an inverse Fourier transform scheme. So in this scheme, we process the first 2 dimensions, linear predict and process the 3rd dimension, and then inverse process, linear predict and reprocess the 2nd dimension. And the point of this is that we only apply linear prediction to a given dimension when the other dimensions are already Fourier transformed. So I'm going to execute this script now. And for those of you who are curious about this, the processing is taking place on a Linux virtual machine on an Asus laptop with an Intel i7 processor. Okay, so that processing is finished. We can look at individual planes, or we can use the command to view strips. And now this time, we will see the original data, the Fourier transform data, which is in blue, and the corresponding linear prediction data, which is in green. So it's nicely narrower in both directions now. So that's nice. So let's say instead of linear prediction, we would like to use one of these special reconstruction methods. So this time I'm going to use the SMILE reconstruction method. And I will generate a new processing script accordingly and execute that script. Now SMILE, as you may recall, starts by building ideal models in the time domain of signals with a range of different decays and figures out what those ideal signals would look like if they were sampled in the same way as the experimental data and Fourier transformed in the same way as the experimental data. So here's the result, individual planes, and here are the strips. So the regular FT, the linear prediction, and the SMILE results. And the SMILE results are just a little bit sharper even than the linear prediction results. Very nice. And as you can see, it doesn't take very long to do it, and it's no more difficult using this interface. So that's a conventional example. And what we can also do if we want is in the NMRPipe command panel, I'll use the option for peak detection. Set the number of dimensions to 2. And I'll press the button to detect peaks. And now we have a 3D peak table for this data set. So very simple. Next, I'd like to turn my attention to a non-uniformly sampled case. So we'll work directly with a 3D example. The example we're going to look at today is an HBHACONH experiment. Now, in the case of converting non-uniformly sampled data, in addition to specifying the name of the spectrometer input, we also have to specify the name of the non-uniformly sampled schedule file. It contains the schedule used to acquire that data. And that schedule is just one or two columns of integers, 2 columns for a 3D data set, and that's used as input to the conversion. And so now, when we run NMR draw, we have a case like this. So here's the first 2D plane of that time domain data. In this case, it's mostly fully sampled. If we look at some other planes, then we'll begin to see the sparse sampling. So for example, this is plane number 3, and you can see that some vectors have data and some vectors are just empty. when we have non-uniformly sampled data, we get a converted version of the FID that has all the missing parts filled with zeros. And we also generate something called a mask, which is the same size as the original time domain data, but the mask has ones in places where data was measured and zeros in places where data was skipped. So this mask is used as input for some of the reconstruction methods. So let's go back to our time domain data. And just as we did before, I'm going to choose the first horizontal slice in the first plane, Fourier transform it, and choose a phase correction value. And then I'm going to generate scripts using this phase correction value. And the first thing that I will do is execute a regular Fourier transform scheme on this data. So we can do a regular Fourier transform on the non-uniformly sampled data. And it's not very informative if you look at the 3D, but the 2D projection can be used to check that phase correction is okay. So here's the XY, and here's the XZ projection. And when I look at the XZ projection, I see the situation that we saw before, that the center of the spectrum has been rotated to the edges. So that's in the H alpha, H beta dimension. And so I have to change the Fourier transform options for the H alpha, H beta direction so that the two halves of the spectrum will be rotated back the way they belong. So I've turned on that checkbox. I'll update the scripts. And now I'll execute the FT script again. So again, the 3D transform is not particularly useful, but looking at the projections is. So the XY projection looks good. Now the XZ projection looks good. And the YZ projection looks good too. So I'm comfortable with the phase correction values and all the Fourier transform options. So now I can execute a non-uniform sample scheme. And I'll choose SMILE as the reconstruction technique. Update the scripts accordingly. And now I will execute the script that does a complete non-uniform sample reconstruction. So SMILE is operating now and going through its iterations. At each iteration, it models the largest peaks and fills in the blanks for those particular signals. SMILE calculation is finished. And now let's look at strips of this result. So I have this set up so that we can also view versions of the fully sampled data. So, for example, this first pair of strips is from a fully sampled version of this experiment. And then the corresponding pair of strips is from the non-uniformly sampled version, which was sampled at 33% density and processed with SMILE, which both reconstructed the data and extrapolated the data. So we actually have a result here that is sharper than the corresponding uniformly sampled spectrum. So you can see the results are beautiful. They're easy to perform. And you can try them too. So that's today's overview. I invite any of you to send questions now by chat, and we'll talk about them. And of course, you're welcome to write at any time. In any case, I hope this presentation was useful and interesting, and I hope the software is useful for your work too. Thanks very much.
Thank you, Frank. It was a very interesting seminar. Even for somebody who's not an NMR person, I found that very interesting.
Thank you.
And so if we have any questions from the audience, then please feel free to put them in the group chat window in Fuse. Oh, and looks like we have a question. So we have a question from Marcus. Is there a baseline correction option?
That's a great question. There is indeed baseline correction options. In the case of amide detected data, which is marked by a directly detected dimension that is labeled HN, by default, the processing scheme will have a convolution solvent subtraction filter inserted, and also by default an automated fourth order polynomial baseline correction inserted. And that baseline correction is applied after the first two dimensions have already been Fourier transformed. You can change those options from inside the graphical interface. You can choose between a convolution solvent filter or a polynomial subtraction solvent filter or none. Or you can change the baseline correction order or turn it off. And of course, since you have full access to the processing scripts themselves, you can always rearrange the baseline correction functions if you need to do something more extensive than what's done just by the default versions of the scripts. So that's baseline correction.
All right. And we have a question from Michael. I guess we can use any data sampled with any collection strategy, including Brooker MDD.
That's correct.
Okay.
We don't have scripts. We don't have scripts to do MDD reconstruction in NMRPipe. Although the native MDD software uses an NMRPipe workflow, but none of that MDD software is embedded in NMRPipe.
Any other questions? Not seeing any. So again, thank you very much, Frank. That was a great seminar.
Yay, thank you very much.
And thank you everybody for attending.